Hello, so I am following up with another short video to assist in working through assignment 3, and this is going to provide a brief introduction as to how we deal with qualitative or nominal variables using what we refer to as a series of indicator variables. Okay? And so in research studies, oftentimes we will confront variables that may be qualitative in nature. And so in those instances, we basically need to think about a way in which we can code those variables such that they could be incorporated directly into our regression analysis. And so in this context, what we want to do is basically assign a unique number to each possible category that that variable can take. And so we'll generally refer to this as creating a series of 0-1 indicator variables or dummy variables or binary indicator variables. And as an example, we can think about a predictor such as marital status. And so we can code that X variable to be equal to 1 if a person is married and 0 if they're single. And then as a consequence, we can include that in a regression model to see what differences we would see between married and single persons as it relates to some dependent variable of interest, okay? And so in doing so, traditionally we'll assign a value of 1 to the characteristic of interest if they meet that standard and 0 otherwise. So generally speaking, if the condition is true, we set the variable equal to 1. If the condition is false, we set that variable equal to 0, okay? We can expand that in several different settings. And so for example, we could take a continuous variable like income level, and we could break that into a series of discrete categories. And so as an example, let's assume we're looking at income ranges, and those data may be essentially continuous, but there may be advantages for us to break them into a series of categories. And so as an example here, we can take a continuous income variable and create a 5-level categorical variable from 1 to 5, where we have cut points of every $10,000 as an example here, starting at a $20,000 threshold, okay? Now, when we do this, it's important to recognize that an inherent assumption here is that the distance between each category is equal as we move up that scale. And so, for example, moving from category 1 to 2 is analogous to moving from category 4 to 5, and likewise for all of the interior categories. And in some circumstances that may make sense, in others it may not make sense, because we may have some relationships that are not consistent in nature, or we may have some categories where those differences are larger or smaller, or there might not be a practical interpretation. So previously in the class, I've used the example of injury severity when you're involved in a traffic crash. And so we typically use a 5-point scale assessing how badly injured an occupant in a crash-involved vehicle would be, but we can't necessarily say that the distance between those categories is equal. So for example, as we go from a crash that results in no injury to one that results in just a possible injury, that step is probably different than moving from a severe injury to a fatal injury, as an example. So we can't necessarily make that same assumption. Consequently, an alternative way of working through this is to create a series of binary indicators to represent those categories. And so looking at the same data that was presented on the preceding slide, instead of one variable that's coded from 1 to 5, here we have a series of 4 variables, each of which are coded either 0 or 1, okay? And so what we're doing here, we're allowing for some additional flexibility in our model. And so, for example, maybe as these income levels increase, we would see some differences in terms of how those people drive, but we wouldn't necessarily see the same impact as we go from category 1 to 2, 2 to 3, 3 to 4, and so forth. And in fact, we may see that some variables, we may tend to see increases in our dependent variable up to some level, but maybe that effect then plateaus or starts moving in the opposite direction. And so we don't necessarily see a consistent linear effect across the categories. And so in this circumstance, we can basically estimate, if we assume there's k levels to a variable, we can estimate k minus 1 binary indicators. Now, we can't estimate 5 indicators for a variable that has 5 categories, because what we're essentially doing here is we're comparing differences across these categories. And so since we already have a constant term in our model, we need to leave out at least one category. And so that constant term would basically represent the average effect if all of these other categories were simultaneously equal to 0, which would correspond to the case to that category that's been left out being equal to 1, okay? And so if we tried to include 5 variables here, we would basically over-identify our model and we would not be able to converge to a solution under ordinary least squares. Now, fortunately, if you try to do this in SPSS, it will automatically kick one of those variables out because it will notice that you're caught in the quote unquote dummy variable trap, okay? And so as we think about assignment 3, there are a number of different variables that are nominal or categorical in nature. And so there are different approaches we can use to try to work through some of these. And so I'm going to quickly demonstrate in SPSS what the implications of some of the decisions we make from a modeling standpoint are. Okay, and so here we're back in SPSS and we have our data set that we've been working with. And one of the most important variables to probably think about at the onset would be our route variable here. So again, we have 3 different routes that each traveler can choose, and that includes an arterial, a 2-lane highway, and a freeway. And so from an analysis standpoint, maybe the first thing we'll do here is just treat this variable as if it's continuous in the manner in which it's coded, okay? And so what I'm going to do here is I'm going to estimate our travel speed as a function of the route ultimately, okay? We won't worry about any of our plots or residuals. We're just gonna look at what the raw effects are here ultimately, okay? And so I'm gonna run speed against route, which again is coded as 1, 2, or 3. And so first of all, looking at our results here, we'll see that that variable ends up being statistically significant. But now the question is, what does that result actually mean to us, okay? So first and foremost, we see a constant term of 19.969. And so a natural question is, what does that number actually mean, okay? So as we all know, we've got one independent X variable in this case, and that's the route, which is coded as 1 to 3, okay? And so that constant represents what the average travel speed is if that variable were equal to 0. Now, from a practical perspective, that is somewhat of a nonsensical result because it's impossible for our route to be equal to 0 because we only see the values 1, 2, and 3, okay? Now, that's not necessarily a problem because we don't need for our constant term to have any meaningful natural interpretation, although I think there are advantages to doing so, and I would generally suggest you try to do that as you estimate your models. A simple way we could do that in this case would just be to recode this variable from 0 to 2 instead of 1 to 3, and we'll demonstrate that in just a moment. But if we think about this in concept, what this basically means is that we're assuming that the average travel speed on Route 1 would be 19.969 plus 3.405. The average speed on Route 2 would be 19.969 plus 2 times 3.405. And the average travel speed on Route 3 would be 19.969 plus 3 times the parameter estimate of that route term, okay? And now, interestingly here, we'll just show how we're going to basically create a new variable, which in our case, we'll just call route recoded. And that's just going to be equal to our route minus 1, okay? And so all I'm going to do here is just rerun that same analysis, and just for demonstration purposes, instead of estimating speed versus route, it will be versus the route recoded variable. And so interestingly here, what we'll see is that our constant term is now increased from 19.969 to 23.374, okay? Interestingly, we'll see that the actual effect here is still 3.405, and the only thing that's happened here is that our line has basically been shifted up in this case, and our y-intercept is at a higher value than it was previously. As we try to determine the means within each of these categories, we now have the first route has an average travel speed of 23.374. And so that's directly reported here as the constant term. The average speed on Route 2 would be 23.374 plus 3.405. And the average travel speed on Route 3 would be 23.374 plus 2 times 3.405. Okay? So ultimately, we would end up coming to the same conclusion in this circumstance. However, the only difference from a practical perspective is that the constant term has meaning in the latter case and not necessarily in the former. Okay? Now, the other question that comes into play here, though, is let's say if we look at a plot of these data. So if we look at our average travel speed as a function of that route, and we might want to look then at what that plot looks like. Okay, and so just from looking at this, the way we've treated the variable up to this point, assume that it is continuous, basically assumes that we have a straight line linear relationship between the mean values here. And so that's not particularly easy to see with the scatter plot here, although it does look like perhaps the distance between groups 3 and 1 and 2 between that route is larger than the difference in speeds between routes 1 and 2. So we may be making somewhat of a tenuous assumption there. Another way we could look at this is instead of treating this as a scatter plot, we are basically going to look at this as an error bar plot, okay? And so what we're doing here is this is basically plotting out where the mean speeds are within each of those 3 groups, and we also have 95% confidence intervals. And so if we think about this, previously when we had looked at these variables, we were basically assuming that we saw consistent increases as we went from route 1 to route 2 to route 3. As it turns out here, speeds actually decrease slightly on route 2 as compared to route 1, and then they increase on route 3. So if we assumed a strictly increasing relationship, we're significantly introducing some problems in our model here, and we'd end up with biased estimates as to these differences as a consequence, okay? So that's a problem. And so what we're going to do instead, I'm going to use the transform recode into different variables. And so what I'm going to do here, I'm going to take that route variable and I'm going to create a series of indicators. And so route 1, so I'm taking the route variable, I'm creating a new variable called route 1, and then I'm recoding this and I'm saying anytime the value in the existing route variable is equal to 1, I want this new variable to be equal to 1. In all other cases, I want that variable to be equal to 0. Okay, and so I'm going to hit continue, okay, and that variable has been created. I'm going to do the same thing with each of the other routes. So I'm going to create a variable called route 2. That will be equal to 1 whenever that initial variable was equal to 2. And again, in all other cases, I'll have that equal to 0. Hit OK, and that's been done. And we'll do the same thing one more time. And so this time for route 3, if our original route variable is equal to 3, we want our new variable to be equal to 1, or otherwise it's equal to 0, okay? Now I've purposely created more indicator variables than we actually mean here, just so I can demonstrate what SPSS will do when we try to estimate these models. And so we're gonna go back. We're going to estimate a linear regression model. And in this case, we're going to include those 3 binary indicator variables. And we're gonna hit OK. And what we're going to find here, interestingly, we find that only 2 of those variables have been included in our model. So it's arbitrarily made the decision to throw out route 2. And so as we look at these results, what that means in practical terms is this constant term here is representative of what the average speed on route 2 is, okay? So on average, the speed on route 2 is 24.5 miles per hour. On route 1, its average speed is 2.388 miles per hour higher than we see on route 2. And so that would give us an average travel speed of roughly 26.9 miles per hour. And on route 3, that average travel speed is 13.4 miles per hour higher. So that's going to be around 38 miles per hour, okay? And we can also make qualitative, or in this case, even quantitative comparisons between the routes. And so the difference in speeds between routes 3 and 1 is just 13.435 minus 2.388 as an example, okay? And so this should reinforce to us certainly that we do have a somewhat nonlinear relationship with respect to that route variable. And that should make sense because it was just arbitrary. We decided this is route 1, this is route 2, this is route 3. So there's no reason for us to necessarily anticipate that as that variable increases from 1 to 2 to 3, that we'd see a meaningful and consistent result in terms of what the effects on our average travel time are, okay? Now, interestingly, that same phenomenon should be considered when we look at some of our other variables, okay? So even if we look at things like the age groups or the income groups, when we actually look at the distribution of those variables, and so I will just use, let's say, our income category as an example here. So in this circumstance, you'll notice as we go from income category 1 to 2 to 3, we're starting to see it what look like consistent increases. All of a sudden in group 4, we see a drop, and then it increases again as we go to group 5. And so a question that arises here, well, is there something strange about group 4? And so as we look at the way that our data are structured, oftentimes we can determine whether or not to use a continuous variable or a series of binary indicators. And even with the binary indicators, it may be such that we have groups that are very similar to one another. So let's say these are really close. So we could aggregate those two income categories into one bracket, which instead of having incomes less than 20,000, in this case, it would be incomes less than 30,000, okay? Likewise, maybe these two form a group and maybe the fifth category is a separate group. And so we could leave the fifth category out and work with a series of 2 binary indicator variables instead of 4. And so there's a myriad of different ways we can do this. Unfortunately, there's not a nice, easy algorithmic way to just go through all of this. It's largely through brute force and using your own knowledge and understanding of the data in the topic area, okay? But hopefully this is helpful as you think through estimating your models for assignment 3. And if you have any other questions, just let me know.